Alrighty, now for the last part of this video. Now we're going to continue. I made it in three parts originally, so to make sure I was doing everything right. Action potential. So now, after the graded potential, we're going to talk about something called the action potential. And so the graded potential helps us reach threshold, but the action potential is when we actually finally hit that threshold point and this action, this wave moves down the axon from the axon hillock, as I highlighted right here, all the way to the end. Okay, so there's a few things that happened. The first thing that happens is once the sodia, or yeah, once the graded potential heat hits threshold, so we go from, I'm gonna do a little bit more, negative 70 millivolts, and we move up to negative 55 millivolts. This is when we can start this wave of action that moves down the action and releases neurotransmitters and moves it down to the next neuron. And this is all because we finally hit this this negative 55 millivolts right here in the action potential in the axon hillock. That's where it starts first because the axon hillock have a super high concentration of sodium gates. So that's why this is important. Um, so once we hit this negative 55 millivolts, this gate actually, this activation gate opens and it allows sodium. These little purple pluses are all going to be our sodium particles. They're going to rush into the cell and they're going to change the inside of this cell. They're going to change it from negative 55 millivolts to about positive 30 millivolts. And that's because it's bringing all of these positives in with it, all these positives. And this charge difference, because we remember this part of the cell over here, this part of the, I don't know if you can see this on the board here, but this part of the cell over here is still negative. And so this changing of charges is going to move. Okay. And as this as these positives start changing the electromagnetic gradient of the cell, it's going to continue to open these inactivation gates. So these inactivation gates are going to open. So they're going to have these open gates here, and more sodium again is going to rush into the cell. Okay, and so we're just going to get this continual change of sodium rushing into the cell, and it's just these positive charges moving down and down and down the axon. And it's going to continue this until it changes this entire neuron to this positive 30 millivolts, and that's kind of where it's going to stop. But the last thing that's important too is you see over here I have this blue channel. This is our calcium channel, and what's going to happen is as this threshold moves closer all the way down here to positive 30 millivolts, what it's actually going to do, let's rewrite this, 30 millivolts, is it's actually going to open up this calcium channel and it's going to allow calcium to rush in. And when calcium rushes into the cell, this change in polarization is actually going to cause these little things called snare proteins. Snare. So these little snare proteins are actually what they're going to do is they're going to bind to these little vesicles right here. So these are little snare proteins that are activated by calcium. They're going to bind to these little vesicles full of neurotransmitters. Let's say this is like acetylcholine or something. We'll just call this ACC, acetylcholine. I don't know if that's the actual abbreviation for it, but that's what we'll call it for now. It's actually going to bind to these little vesicles, and the um, the membrane's actually going to open up, and it's going to engulf these vesicles through exocytosis. We talked about this a little last week. And it's going to allow these vesicles to exit the cell and allow the neurotransmitter to reach the next it's going to allow this neurotransmitter to reach the next axon, the next neuron, excuse me. And so that's how you get this changing of charge that actually causes a release of neurotransmitter in order for like a thought or a sense or anything to be realized, and it's all because of this action potential. Now, as interesting as this negative 50, or excuse me, as this positive 30 is what um so excuse me, I kind of misexplained this actually a little bit earlier. um as the cell moves from this negative 55 millivolts to positive 30 millivolts, the negative 55 millivolts, right, is what opens up these channels, right? However, once they reach positive 30, they're not going to just continue to get more and more and more positive. There's a point at which this little ball and chain is actually gonna swing shut, and it's gonna start closing. It kind of works on a timer. At least that's the way it was described to me. That sort of made sense. Is the second the voltage is reached in order for it to open, the other one starts to slowly close. And now slowly is relative. It closes very fast, but um, relative to the movement of the signals, it just slowly will close behind it, and it'll stop this influx of sodium. Now, although this positive 30 millivolts is what shuts this gate for the sodium gated voltage channels, it's actually this positive 30 that opens the potassium channels. And so now this potassium channel wants to return to resting membrane potential. And so what this is going to do is it's going to open these potassium gated voltage channels, or these voltage gated potassium channels, excuse me. And so now this positive charge is going to cause a bunch of potassium to leave the cell. And that leaving of the cell works very similar. It's going to start bringing this positive 30 millivolts on the inside of the cell back to actually about negative 90 millivolts, which is a lot more than negative 70, which is where we're at RMP, right? And so this is what we're going to call hyperpolarization. And this hyperpolarization is just due to the fact that when this positive threshold, this positive 30 millivolts threshold is reached, and these potassium gates open and potassium begins to flood out of the cell, it's going to flow out very quickly, and kind of similar to the way the sodium gates work, is it's not super fast. And so when it finally does shut, it's actually let out more sodium, or excuse me, more potassium than it needed. And so that's where you're going to get this negative 90 from, is because it's going to hyperpolarize. It's going to become more negative than it was originally intended to. But due to the sodium potassium ATPase pumps and the leak channels and everything, eventually it'll return back to that negative 70 millivolts, which is obviously our resting membrane potential. And so that's kind of how this whole process of an action potential works. And so um, what we'll talk about too a little bit is kind of what this looks like on a graph a little more. There's a few. Oh, I'm gonna try to change this. Try a graph here. Okay, this is our graph, and this is going to represent milliseconds and millivolts. Okay, here's our negative 70. Here's our threshold potential. And we'll write a couple numbers out here. This is our threshold potential. This is our resting membrane potential. And yeah, so I'll kind of re-explain everything that I was talking about up here down on this graph and kind of what this looks like when we see an action potential on a graph. So to start, here I'll do it in blue. To start, we have resting membrane potential right here at negative 70 millivolts. And we're going to get this increase in charge through our EPSPs, right? So our EPSPs are going to continue to summate, 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 summate. And finally, once we hit this point, this is where those sodium gated, or excuse me, the voltage gated sodium channels are going to open. Once we hit this negative 55, and sodium is going to rush into the cell super fast. It's not going to go quite that high. Okay, so we're going to get all the way up here. We'll say this is like positive 30 millivolts. Okay, up there, and those sodium gates are going to start to close once the voltage changes and you have that conformational change, which is going to change the shape of those sodium gated, or the voltage gated sodium channels. And what we're going to see is we're going to see that drop back in voltage as potassium starts to leave and leave and leave and leave the cell. And as it leaves, before those gates close, we're going to see this dip. Okay. And this dip is like I was talking about up here. This is where we're seeing this hyperpolarization. The sodium's leaving, and before that inactivation gate on those voltage gated potassium channels can close, we're going to see more potassium leave than we need to until it brings itself back up to resting membrane potential, and then we'll see it continue on. So there's a few important things to identify here. Okay. The first thing is we're going to identify this as the depolarization. Okay. So this is when it's going from negative 70 to positive 30. It's getting less negative. And so this is where we see it, the depolarization, where we see that axon start to depolarize. Um, and then once we reach this peak, obviously those sodium gates begin to close, and sodium will no longer be let into the neuron, and we're going to see this area over here on this side, and this is where we're going to call this the repolarization zone. And this is when the the cell gets closer back to resting membrane potential. It's returning to its original state. Now this dip is what we're going to call hyperpolarization. Obviously hyper meaning more polarization. And then obviously the return back to resting membrane potential. And so what we're going to see here is there's a few other areas that we got to talk about. Number one is if we were to draw a line right here, this area right here is called our absolute refractory period. And the absolute refractory period is important is because this area identifies the fact that no matter how much voltage you stimulate the cell with, you're not going to get an additional action potential until after the cell has returned back to resting membrane potential right here. Now, there's this other area right here where if you wanted to stimulate an action potential, you would have to do it even more. So instead of moving the cell just from negative 70 to negative 55, so that'd be what, 25 or less than 25 voltage, that'd be 15 voltage, right? Yeah, 15 voltage. Man, I cannot do math clearly. Um, you would need even more additional voltage in order to stimulate an action potential. And so it's very unlikely that this happens, but it is possible. And this area is called the relative refractory period. And the relative refractory period is in a time where you could there could be another action potential immediately after this one. But in order for that to happen, you would just need additional stimulation than the original amount required until that cell reaches resting membrane potential. Now, cells, yeah, so obviously this all happens very quickly, and there's a few things that can make it happen even faster. And that is what we called myelin. And so like in a axon, is our myelin sheath here. Our myelin sheath here. And so when you have an action potential proceed, myelin is actually going to cause this signal to move even faster. And I'll explain why that is. So here, I'm going to add a little. This is our sodium channel. Sodium V channel, and we're going to have another sodium V channel here. Um, so across the membrane, like I was talking about a little bit earlier, you have these potentials, and potential just means having charge. And so with these charges are going to actually affect how far, when you get sodium that rushes into the cell, it's going to kind of release this signal, right? And as it was described in classes, it's called a Bwong or the length constant. And the the length constant essentially describes how far down the axon the signal will propagate until you need additional stimulation to further the charge, or excuse me, to further the signal. And so when you have these areas of myelin, there's actually a greater separation of charge and less overall charges between the membrane. And so what this does is this actually causes the Bwong, the length constant, to here we'll write this here, length constant. This actually allows this length constant to move farther and to move faster because there's less of these charges right here that are inhibiting the movement of this Bwong. And that's something we call capacitance. And so when you have a greater separation of charges, you have reduced capacitance. And so essentially what these areas of myelin are is the it's a way for the cells to travel further without needing additional propagation from sodium channels. And so yeah, myelin just essentially helps the cell propagate these action potentials even faster, um, without needing, the additional introduction of sodium. So now instead of having sodium channels, like every here and here and here, you just need them, spread out more. And so, yeah, that essentially allows the action potential to travel further before it needs additional aid from sodium channels. Um, and essentially just reduces the charge across the membrane, which means that this length constant has less things to worry about or flip or have interrupt its charge. For example, a lot of the times, like even the size of the axon that can affect the length constant. Because if you have a larger width of an axon, these little proteins in here that naturally sit in between the membrane, they have a negative charge. And so this Bwong obviously is gonna hit these axons. And so, or not these axons, it's gonna hit these little proteins. And so when you have a wider axon, there's more space for this Bwong to the length constant to travel down the axon, and there's less things that are gonna interrupt that charge. Or interrupt that action potential. And so yeah, that should be everything. Thanks for listening.